Welcome. Now we're going to take a look at the gas laws quiz. Question number 1. In a heating curve, two plateaus may occur. These two plateaus are, which of the following? Now, a heating curve, first of all, what does one look like? You can draw the y-axis here, the x-axis here. In a heating curve, this is energy. Okay, the energy is going to increase as we progress to the right. And on the y-axis, we actually have the temperature. Okay. For a heating curve, the general shape is going to increase as we add energy initially. The temperature will increase. We'll reach a plateau where we'll be inputting energy without increasing the temperature. Then the temperature will begin to rise as we input energy. It will flatten out again. Temperature will remain constant. And then after that, the temperature will rise again. What's going on in these three cases? Here, below this line, we'd be looking at a substance in a solid state. As it plateaus and then begins increasing again, we enter the liquid state. Plateaus again, it starts rising again. Now we're in the gaseous state. So this is a heating curve showing the transition from the solid to the liquid to the gas phase. These two plateaus, what's happening in these two plateaus? Well, first and foremost, we are adding energy in both plateaus. Throughout the entire graph, we are adding energy. So A, yes, we're doing that. B, are the result of a phase change from solid to liquid? Well, from solid to liquid, that is one of the plateaus, but the question talks about and refers to both plateaus. So that's right, but only for half. Are the result of a temperature remaining constant? Is the temperature increasing in the first plateau? No, that's why it is a plateau. What about the second? Here, is the temperature changing? The answer is no again. That's why it's the second plateau. So it should be A and C are correct. E would be your answer. In a phase diagram, the critical point is defined as the point in which a solid is no longer distinguishable from a gas, a solid is no longer distinguishable from a liquid is no longer distinguishable from a gas, or all three of phases of matter coexist. Let's take a look at it. Again, it'll be a graph. The general shape of our phase diagram is going to look a little bit like this. It's going to increase, which place we're going to have a point. It's going to come out like this. There's going to be another point. And then this guy is going to be a relatively straight line extending on forever. What are my axes? Well, here we'll have the pressure. And here we'll have temp. Okay. The question here is assessing the critical point. This is the critical point. All right. What's happening there? Well, as you may recall, this is the gaseous phase. This is the liquid phase. and this is solid. So the critical point would be the point at which a liquid is no longer distinguishable from a gas. The answer would not be B. The answer would not be A. 2, all three phases of matter coexist. That is not the case. This point here is the triple point, TP, triple point. That is where all three phases of matter coexist. Number 3, 100 Celsius is equivalent to blank degrees C plus 273 equals blank Kelvin. All right, that's the formula for converting from Celsius to Kelvin. Input 100 there, you end up with 373 Kelvin. Little side note, you notice there's never a degree mark with Kelvin. Okay, there's only degree marks for Celsius and Fahrenheit. Standard temperature pressure, STP, is defined as not 373 Kelvin, not 101.3 kPa. 273 Kelvin, that is accurate. 1 ATM, that is accurate. 273 Celsius, no, it's 0 Celsius. 760 millimeters mercury, yes, that would be accurate for standard pressure. 373 Kelvin, no, 273 Kelvin, 0 Celsius. 101.3 kPa, yes, that would be accurate. So any of those three pressure scales, or that temperature, or 0 degrees Celsius, that would also be acceptable. Next, we're going to look at the questions revolving around Gay-Lussac's law, Boyle's law, and Charles's law. Gay-Lussac's law relates pressure and temperature. A decrease in pressure will result in a decrease in temperature because they're inversely proportional. That's incorrect because they are directly proportional. Okay, must say directly proportional. Since they're directly proportional, a decrease in pressure will result in a decrease in temperature. A decrease in pressure will result in a decrease in temperature because they are directly proportional. The answer here is B. Boyle's law relates pressure and volume. A decrease in pressure will result in an increase in volume because they're inversely proportional. Yes. Okay, they're inversely proportional. Since they're inversely proportional, a decrease in pressure will result in an increase in volume. If you think about this, we could take a balloon, okay, take my balloon, and think about what if I decrease the pressure, all right? So the pressure is going to decrease, less pressure, not in just one spot, but in every single spot. What would happen to the volume? A decrease in pressure results in an increase in volume. As pressure goes down, V goes up. Charles' law relates volume and temperature. If you look at the notes from Charles's law, volume and temperature are directly proportional. All right, so let's key in on it. Directly proportional or directly proportional. a decrease in volume will result in a decrease in temperature. All right. My tip to you, when you're provided with a law, know that the variables are either directly or inversely related, and then pay attention to the next thing. All right. We know that volume and temperature are directly proportional. So it's one of those two options right up front. Then it should just, since it's directly, it should just do the exact same thing, a decrease in volume, decrease temperature. Question 8. Sorry. All right. Question number 8. Which of the following is not true of the gas laws we have encountered? Any pressure scale may be used. That's true. Any temperature scale, including Celsius, Kelvin, or Fahrenheit, may be used. That is not true, okay? Because Celsius cannot be used, Fahrenheit cannot be used. The absolute temperature scale, Kelvin, is the only temperature scale that should be used. Kinetic molecular theory explains that the behavior of a system depends on combined action of molecules. Indeed, and negative motion is impossibility. Therefore, it's impossible to have negative amount of kinetic energy. That is true. Remember, average kinetic energy is temperature. Okay. So when we're talking about negative motion here, since you can't have negative motion, energy is the energy of motion, or sorry, kinetic energy is the energy of motion. You can't have negative motion, so you can't have negative energy, so you can't have a negative temperature. That's exactly why we have to have the Kelvin scale. Okay, Kelvin is a necessity because it defines absolute zero. You cannot go colder than you cannot go colder than 0 Kelvin because you can't have a negative temperature, because you can't have a negative energy, because you can't have negative motion. Okay, now we're going to review the graphing portion of the final exam. We'll take a look at determining absolute zero graph. This was constructed straight from data collected during class. We had the metal sphere and a pressure gauge attached to that metal sphere. In addition, we had a hot water bath set up and also a bucket of ice water set up. You can see that the higher temperatures here are associated with relatively high pressures. And the lower temperatures, this is where the sphere was submerged in the ice water, we have lower temperatures correlating to lower pressures. The pressures were in units of PSI, the temperatures in units of Kelvin. Now, on the exam, what we should expect to see are possibly 4 different styles of questions. One style of question could be simple, where I could ask you, what would be the corresponding pressure when the temperature is approximately 125 Kelvin? All you'd have to do is go up the temperature scale to approximately 125, all right, right around in here, and right around in here, and then shoot that over and drop it down. As soon as it intersects that trend line, we'll know the predicted pressure. In this case, the predicted pressure would be 6 psi. Now that's a pretty simple question. That's the typical graphing question that you have seen before throughout your science career. What we're going to do, though, is something a little bit better, a little bit bigger. First and foremost, which gas law relates temperature and pressure? Okay. Which gas law relates those two items? Of course, you may remember that your options are going to include Boyle, Charles, or Gay-Lussac. If you guess anything other than one of these three, that you're way off track. But Boyle's law, you'll be looking at pressure and volume. Charles's law, you'll be looking at volume and temperature. Gay-Lussac's law, looking at pressure versus temperature. So this graph is one that we'll be looking at the Gay-Lussac law. Right? It will not look at Boyle's or Charles's law. Gay-Lussac's law, that's the one we're paying attention to here. And Gay-Lussac's law also, a little side note, what is the relationship between pressure and temperature according to Gay-Lussac's law, according to the data collected by the classes? So, what is the relationship? Between your variables? Okay. Let's see what happens. Well, a relatively low temperature corresponded with a relatively low pressure, whereas a relatively high temperature corresponded with a relatively high pressure. This is indicative of a direct relationship. As one increased, the other increased. What is some supporting evidence of this direct relationship? Some supporting evidence of the direct relationship is the m in your equation. An equation has a general form, y equals mx plus b, where m is the slope of your line. That's the slope of this trend line, 20.098. What is the slope? The slope is defined as the rise over the run, or in this case, the rise, the temperature, over the run, pressure. Okay, now what does that mean? If our slope is 20.098, positive 20.098, that would be like 20.098 over 1. So every time the temperature increases by 20 units, the pressure should increase by roughly 1 unit. Here we have our pressures right around 14, okay, in that ballpark, going up to about 17. That's an increase of about 3 pressure units. If the pressure increased by 3, the temperature would have to increase by how much? 3 times 20, roughly 60. If you look here, our temperatures are grouped just under 300 for the first set. For the second set, we're going from 350 right around 350. So that works out that's a rough estimate, but a fairly good rough estimate. The temperature difference was about 60 Kelvin from our high to our low. Last bit of questions. The last bit of questions could surround the plus b value. The plus b portion is, as you may know, the y-intercept. And what does the y-intercept tell you? All right, this is going to be, it's where your x value becomes 0. The point on y, the point on the y scale, the temperature scale, at which the pressure goes to 0. What is that? Is it 0, 0? No, it's not 0, 0. It looks like it intersects at 0, 0, but it is not. It is negative 0.308. Okay, the y-intercept is negative 0.308. What does this tell you? Okay, this tells you the predicted value of absolute zero based on our data. Okay. Predicted value, negative 0.308. Now, why can't you see negative 0.308? Well, look at the scale of this axis. Okay, we're looking at this much being 50 units. All right, that's 50 units. Are you actually going to be able to see visually 0.3 units? Of course not. All right, of course not. So that's why it looks as if it intersects at 0, 0, but it does not.